the first lecture of a series about matrices, and we will start with the definition of a matrix in mathematics. We start with the following objects. So we first define a collection of real numbers such that to every real number is associated a precise place in a two-dimensional plane. Okay, so let's assume to have a collection like this: number 1 here, number -2 here, number 0 here, number 3 here, number 4, and number -1. Okay, so now we have certain real numbers that happen to be integral numbers in this case, and to each there is a particular place in the plane that is associated to. Okay, so how we describe the place this one is associated to? So normally we consider this collection inside like a rectangle. Therefore the first coordinate of the rectangle here on the top row on the left will have coordinate 1 1. As we move right bound along the first row, we'll be moving the first, so let's say this is empty spot, there is no number, but would correspond to a place in the plane 1 1 of coordinates 1 1. As we move along the first row, we will be changing the second coordinate, so this corresponds to 1 2, this 1 3, 1 4. So this then is going to be, so as we move downwards in the first column, the first coordinate will change, so this will have a coordinate 2 1, this 2 2, 2 3, 2 4. Okay, if we take this as an object, mathematical object, so this set of numbers placed in certain positions in a plane, always the two coordinates will be positive and will be integers, okay, starting from 1 1 onwards in both coordinates. So if we take another object of the same kind, so let's say we start with 2 and then 0 and then 1, and then let's say -1 and then 0 and then again -1. Okay, so you see this object is similar, so it's a set of numbers, a collection of numbers placed in certain particular position. The positions are the same, so these two correspond to a place of coordinates 1 2. This 0 will correspond to 1 3, and so on. So let's assume to have two similar objects. We can actually define a sum of them. In what way? We just sum coordinate wise the real numbers that we have here. Okay, so in the first position there will be nothing appearing because there is nothing in the first and nothing in the second. Then in position 1 2 we will have 1 plus 2, so we'll have a 3. -2 plus 0, it will be -2. 0 plus 1 will be 1. Then second row we have a 3 plus -1, it will be 2, and then nothing here. 4 plus 0 4, -1 plus -1, -2. Okay, so component wise we can sum two objects like this. Not only that, we can actually multiply an object like this by a scalar. So if we take this object here, I'm not gonna rewrite it, and we multiply on the left by a real number lambda. Okay, so we have the same object here multiplied on the left by lambda, where lambda is a real number. Then we will be getting again an object like this, a collection of 1, 2, 3, 4, 5, 6 real numbers placed exactly in the same place as those ones. Okay, so how do we define the multiplication by a scalar? We just define it component wise as we've done the sum. Therefore the first spot will be blank, the second spot will be lambda times 1, therefore lambda. The spot 1 comma 3 will be -2 times lambda, so -2 lambda. And then we have 0 times lambda, 0. The second row we have 3 times lambda, 3 lambda, and then blank, and then 4 lambda, 4 lambda, 4 times lambda. And the last one will be -1 times lambda, so negative lambda. So here we have a vector space structure, so hence we have just defined a vector space structure on the set whose elements are collections of real numbers placed in the spot as described. Let's introduce some notation. So we will call the real numbers appearing in this collection will be called coefficients. So there are two notations. Notation A, the real numbers appearing in a collection will be called coefficients. And B, the placing, the spots the real numbers occupy in the collection will be called indices. Okay, so for example, the number -2 here will have in indices 1, 3. Okay, the coordinates associated to a real number will be called its indices. Let's see a real life example of such a collection of numbers. So how can a collection of numbers and the information of the placing of these numbers in a plane can be a good model for anything in real life? Okay, so example, let's say real life example. These are digital images. Okay, so what is a digital image? In practice, a digital image is obtained taking a device made by silicon, actually tiny pieces of silicon called pixels, and one has several millions nowadays of them, and they are placed in a rectangular shape, and this rectangular shape is called the CCD, or let's say through these devices called CCD or CMOS. Okay, so these are these rectangular collections of pixels made by silicon, and each of them captures a certain number of photons, and they are being quantified by a number. Usually the number is comprised between 0 and 255 for each pixel. Okay, so an image basically is a collection of integral numbers, positive integral numbers. They are comprised between 0 and 255 if the image is digitized in 8-bit. And the is not just a collection of millions of numbers, but to each of these numbers is associated a specific position in the CCD. That is what makes the image. Okay, so is just having a certain subject placed in a certain position of the CCD. That means that we have to record both the intensity of the luminosity of the object and the placing of the object in the plane. Okay, so in that case we will have a distribution, a collection of real of positive integers comprised between 0 and 255 distributed on a shape, a rectangular shape. But if we do some post editing of the image, for example, if we take a selection of our image inside this rectangular shape, well, in that case we will just be considering a certain number of real numbers, pixels, that are within this closed region, the region of interest we are considering it, and therefore it is helpful to have that the collection of these real numbers is not just rectangular, placed in a rectangular shape, but being arbitrary. Like in this case, we may have blank spots inside this rectangular region, let's say. Okay, so an image is a collection of millions of positive integers placed in a rectangular region. But as soon as we select a region and we make some changement just to the selected region of interest, we will be having as a good model this particular collection of real numbers, in which we may allow some blank spots in it. Okay. However, we have to mention the following fact. Mathematically, the word matrix, that is what we are going to talk about in this series of lecture, in this chapter, do not refer to collection of numbers that allow some blank spots in it. Basically, the reason for this is because there is supplementary algebraic structure that is extremely interesting inside certain sets of matrices, which can be defined only if the numbers are placed on a rectangular region without blank spots. So we have seen that we have no problem defining a vector space structure on this more general collection of numbers, but it would be impossible to define a multiplication of any two such objects if we allow blank spots in it. So in practice, we are going to call matrix, so the definition, a matrix is a collection of real numbers placed on spots forming a rectangle. Okay, for example, 1 3 0 1, or maybe 1 0. Even like placed vertically, this is rectangular. A rectangular region has a size of 1 horizontally and 2 vertically. This is a 2 by 2. Another matrix can be a line, just simply a line, 1 1. Okay, so this is another matrix. Or may can be something more complicated, like 2 rows and 3 columns. 0 1 2 3 4 5. This is another matrix. So you see we have no blank spots, and they all occupy a rectangular region.